In the second half of this lesson, we're now going to see how we can take complex numbers and do all of the same sorts of operations that we would do with any other types of numbers, namely adding, subtracting, and multiplying. And then when we get to dividing, we're going to look at some additional tricks that are similar to some things that we did with radicals in our previous lesson. So let's think about adding and subtracting complex numbers first. Well, it's very similar to adding and subtracting algebraic terms. Essentially, you can think of this as, here we go, as two binomial pieces being simply added together. And just like in regular old algebra, we can only combine together like terms. In this sense, when we deal with complex numbers, we're only going to add together pieces that are either both real or both imaginary. So that essentially is what's going to make up our like terms. So first off, I'll just get rid of the brackets, and in this case, we're just adding, so it's really just a string of all of these pieces, and then subtract 2, and then plus 3i. It's just all of these pieces with no brackets anymore. And now I'm just going to regroup or rearrange these so that the real number parts, the 6 and the -2, come first because they can be combined, and the -4i and the plus 3i, I leave at the end because they're going to be combined. So of course, 6 minus 2 gives us a real number of 4, so that's our real number part. And then we look at what the i's are doing. We started with -4 of those, and we add 3 of those. Well, it does the same thing that it would do if it was any other type of variable. We end up with -1 of those, so we just write -i, or -i. Let's try another one now. Here, it's the same idea, except we just have to be careful when it's a subtraction. I'm going to rewrite this as -4 minus 5i, and then remind myself that each symbol inside of the second bracket is going to have to switch. So -3, and then plus 2i. Or in other words, it's like I have -4, and then I'll eventually subtract 3 from it. And then I'll also have -5i, and I'll add 2i to that. It gives me -7 is my real number part, and I end up with -3i. That's my imaginary part. And so again, that overall is what we are referring to as a complex number, something that has either a real part or an imaginary part, or possibly both. And what we're seeing here is that our answers to each of these previous two questions have been something that's combined both, a real number part and an imaginary part. Let's see what happens when we multiply these. Well, we still apply all the same sorts of skills that we would learn when we were multiplying any other types of algebraic terms. Again, just treat I like you would any other variable, but with one extra little fact. So when we simplify, we also want to keep in mind one extra thing. We're going to recall that anytime we see I squared, it's going to be equal to -1. Remember, because I itself is equal to the square root of -1. So that means I squared is the actual number -1. So we need to keep that in mind, because sometimes when we're doing calculations using I, we might realize that I squared pops up somewhere along the way. And that's what's going to make I a little bit different than a regular old variable. Because anytime we see I squared, we'll actually be able to replace I squared with a regular integer, -1. So let's see how that works. So here for this one, again, just think of it a little bit like we were doing, 3x times 6x. Well, if you were doing that, you would get 18x squared, but in our case, we're going to get 18i squared. So again, that step was really just the same thing that you've done with variables and algebraic terms when you multiply them for a few years now, really since grade 9. But here's the difference. I is not just a regular variable. It has a specific meaning, and specifically when it's squared, we can replace it with an actual integer, -1. So really, our final answer here is actually -18. So take a second and really try and process that. We started with a purely imaginary number, and then we multiplied it by another purely imaginary number. So you'd think that everything in this question is just existing in some weird imaginary world that has nothing to do with reality and nothing to do with real numbers. But we actually see that that's not the case. We can start with two things that are imaginary components, but in this case, they multiplied together and they gave us a perfectly real numbered answer. This is the thing that I was trying to talk about in the first portion of the video, that it seems strange to even talk about the square root of -1 because it's not a real number that can exist on the real number line. But if we use a symbol like I to hold on to its value and preserve it, then we may see something like an I squared popping up later. And maybe that actually brings things back into the real number world from things that started as being originally imaginary components. Let's try another thing of this. So now we have the same idea here. Again, it's just like multiplying three monomial terms together. So 2 times -5 times 3 gives us -30 as our coefficient. And now we have I to the power of 3. Now, in a sense, that is a full multiplication. We've created a fairly simple looking form, but it's not the simplest that we can actually write this. Because if we separate out I cubed into separate pieces, for example, I cubed could also be thought of as I squared multiplied by another I. Now, for a second, you might be wondering, why did I do that? Why did I bother? Well, it's because now, if I separate it out that way, this I squared can be replaced with, once again, a specific integer, -1. So it's really -30 times -1, and then I just have one single power of I tacked onto the end there. So the simplest way that I could write this is not actually -30 I to the power of 3, it's actually just +30 times I. So when we have two powers of I, it can be converted into a -1, just the simple integer. When we have more than two powers of I, so for example, I cubed, then break it up so that at least, like we had here, at least two of those I powers can be converted into a -1, and then you may have a remaining power, or maybe more than that, as well, that you can then try and see if it simplifies or tack it on to the end of your result. What about this one now? So we've got a fully imaginary piece inside of our bracket, and then that entire thing is being squared. Well, that means we need to apply an exponent of 2 to each thing that we see. So -3 needs to get squared, it gives us +9. I is squared, so it becomes I squared. And root 2, this is where you have to be careful, the square root of 2 then becomes squared, and so it really just becomes the number 2. If it started being square rooted, but then we square it, we cancel out that operation and it just becomes 2. Well, the 9 and the 2 are just numbers that are part of this big multiplication statement, so we can multiply them. They're just 18. And then we still have I squared. And I promise you that there's no general rule here that says that 18 comes up all the time or that -18 comes up all the time, but this is actually going to work out very similar in terms of our answer here to question A, because you're seeing now, hopefully, that I squared can be replaced with -1, just like it did in question A, and that means the whole thing overall can be written more simply as -18. Let's continue on. Sometimes we may need to use our distributive property, or expand, in other words. So we need to multiply 3i times 2, but also multiply it by 4i. So that may give us possibly a mixture of imaginary terms and real terms. This is going to be 6i plus 12i squared. Nothing much that we can do with 6i right now, but anytime you see an I squared, that should ring a little alarm bell for you now, and it can be replaced. So it's really 12 times -1, or in other words, it's 6i minus 12, which is technically correct, but it's not the way that we tend to leave things. I've mentioned this in previous statements before, that anytime our final number, our complex number, is a mixture of an imaginary part and a real number part, we always put the real number part first. So I'm going to just swap around the order of these terms and put -12 out in front first. And the 6i, remember, is positive, so I would add 6i to that. And again, it is mathematically doing the exact same thing. It's just that our general convention, the sort of language that we all tend to speak in math so that we're all understood, is that we put that real number part first and the imaginary part second. And now we've got two binomials once again, but it's two binomials being multiplied together. Earlier we saw two binomials being added and subtracted, but now when they're multiplied, we have to be very careful about our expansion rules. Remember, I need to expand this in and expand this in at the same time. That's going to give me 4 terms to start with, and then I could possibly try and simplify from there. 1 times 3 is 3. 1 times 2i is positive 2i. -4i times 3 is -12i. And then I would end up with -8i squared. Well, let's do a little bit of combining with the two middle terms and a little bit of simplifying in our final term. So the 3, nothing much I can do with that. I'll just call it 3. But then I started with 2 i's and I subtract 12 of them. I end up with -10i terms. And then the last one is -8. Instead of doing times I squared, we should change that to a -1. So really, that's like 3 minus 10i, and this becomes +8. The positive 3 and the positive 8, I'm going to combine together into one single real number part, which is 11, and then the imaginary part is -10i that gets tacked onto it. Let's do one more of this type, but with an additional little wrinkle thrown in. So I only include this one just as a little reminder that this squared means that the entire bracket has to be squared, so it's useful if we actually rewrite this first. 3 minus 5i times another 3 minus 5i, and then start to expand. So 3 times 3 is 9, then we have -15i, then another -15i, and then what really ends up being plus 25i squared. The 9 we'll leave for now. Let's combine the next two terms together into -30i. And the other one becomes plus 25 times, well, -1 is what we can replace that I squared with. So it's really 9 minus 30i subtract 25. And the positive 9 and the -25 are going to be combined into one single real number term at the beginning. They combine to -16. Then I still have -30i. That's the simplest way that I can write that one. So to finish off, let's talk about some additional things we need to think about with dividing these complex numbers. Now, when complex numbers are divided, it produces something we've seen before, a rational expression. But just like we saw with radicals, we need to make sure that our denominator, for reasons that we won't get into so much in this course, but become really important in future courses, it is very important that the simplest form of this rational expression only includes rational numbers in the denominator, which means that special radical numbers like square root of 2 and square root of 3 can't be in the denominator, and it also means that imaginary numbers can't be in the denominator either. So once again, we are asked to rationalize the denominators of these, and we're going to do that not by worrying about any square roots this time, but we're going to worry about trying to cancel out or eliminate somehow the fact that we have imaginary parts existing on the bottoms of these rational expressions, in the denominators of these rational expressions. Well, we're going to tackle it in the same way. We're going to take each of these rationals and we're just going to multiply them by 1. But we're going to multiply them by a very clever version of 1. So for example, right now I have an I on the bottom of this expression. I'm going to multiply it by I over I. Remember, anytime I multiply by the same thing on top and bottom, I'm really just multiplying by a 1 in disguise. So what is this giving me in my next step? Well, it makes my numerator look more complex because now I have 5i, but on the bottom, I have 2i squared. And for a moment, you might be tempted to think, well, we actually didn't get rid of the I at all. We still have an I on the top and we still have an I on the bottom. But we have an I squared on the bottom, which means we can take this a step further. We have 5i on top, and it's really 2 times -1. So really, that means my bottom number can just be -2. But instead of writing it as 5i over -2, I'm going to just let that negative on the bottom make the entire rational expression negative. So it's really negative 5i over 2. So you can just stick the negative in front of the whole thing. So we would say that that is actually the fully simplified version of that rational expression we started with. And we say that it's simpler in that its denominator only includes a rational number, or one that is not a square root and one that is not an imaginary number. That's the key. Now, remember in our previous lesson that sometimes just multiplying by one simple thing on the top and the bottom, like here we used I on top and I on the bottom, sometimes that strategy doesn't work when the denominator is a little bit more tricky. So example 2 is a situation of that. Now, we not only have an imaginary piece on the bottom, we've actually got an overall complex number on the bottom that has a mixture of a real number and an imaginary piece. Well, once again, I'm going to multiply by a very special number. I'm going to multiply by 1. But I need to make sure that I'm multiplying by the opposite, or what we called in our previous lesson, we called it a conjugate. And now, in this lesson, I'll still use the same term, except in this case, we would tend to call it its complex conjugate, because now it's not just a conjugate using radicals, it's specifically a conjugate that uses complex numbers. So -3 minus I is what we could put on top in both cases. What's that going to give us? Well, on top from here, we have -9i minus 3i squared. On the bottom, what are we going to get? Well, this is where we have to do a little bit of a binomial expansion. So I need to pretend that there's brackets around this and brackets around this, and I'm multiplying it term by term. That would give us 9, and then plus 3i, and then minus 3i, and then minus I squared. Now, here's the power of this conjugate. I multiplied by this weird looking thing, but look what it did in my denominator. First of all, I've got these two middle terms that do have an I attached to them still. And I might be upset by that because my whole goal was to try and get rid of those imaginary pieces on the bottom, but as soon as I look closely at them, I should be a bit more happy because I realized that those are actually going to eliminate one another. Those are going to disappear in my next step. But then I also have this other piece that has an I as well, but it's actually an I squared. So I can replace that with something that's not imaginary at all. So my top is still going to be imaginary. It's still -9i minus 3i squared. What do I have on the bottom? Well, I have 9 minus -1. So let's continue and try and finish this off now, a little bit simpler. Not only that, I can do a bit more simplifying on the top. Be -9i minus 3, and I might as well replace that I squared with a -1 as well. At first, I was just focused on trying to make sure my denominator got rid of all of those i's, but now I might as well try and make my numerator simpler as well. On the bottom, when I start with 9 and I take away -1, I actually go up by 1 to 10. So now, the simplest way that I can write all of this is really, well, it would be like -9i plus 3, but I'm going to switch around the order of that and put the +3 first the minus 9i second, and the whole thing, after all that, is over 10. So we started with something that, again, had not just an I on the bottom, but it had an I with multiple pieces to it on the bottom. And so we had to multiply that denominator by its complex conjugate. And we can do that as long as we're really multiplying by an overall fraction that has the same complex conjugate on both the top and the bottom. As long as we can do that, we eventually end up getting rid of all of our imaginary pieces on the bottom and end up with something that we just need to simplify a little bit on top. Let's try that process one more time. So now for this one, again, we're going to multiply by the complex conjugate, which means I focus on its denominator first, and I think about what would be a denominator that has the same pieces, but the opposite sign. Well, it would be 1 plus 2i. And as soon as I decide that that's going to be the bottom of my fraction here, I just make sure that I'm multiplying by the same thing on top. So really, I'm multiplying overall by 1, but it's a fancy one in disguise. Now let's start to expand. So on top, I've got some work to do as well. I'd get 2, and then plus, and then 2 times 2i would be 4i. And then 3i plus, or 3i times 1 is plus 3i. And then 3i times 2i is plus 6i squared. On the bottom, we'd have 1, and then plus 2i, but then minus 2i, and then minus 4i squared. Let's do some simplifying now. On top, we can call this 2 plus, well, that would really be like 7i, plus 6 times, I'm just going to say 6 times negative 1, because I squared is negative 1. On the bottom, I really just have 1, subtract, and the 2i's, the positive 2i and the negative 2i have canceled one another out, so I still have minus 4 times, and once again, I'll put negative 1. So that means I have 2 plus 7i minus 6, so I'll have 2 real number pieces on top I can combine. On the bottom, it's really going to be 1 plus 4. So as a final statement, we could say it's negative 4 plus 7i on top over 5 on the bottom. And that's the fully simplified way to write that expression. Again, don't try and stress too much if the understanding of what a complex number truly is and how to picture it in your mind is something that's tripping you up a little bit. Focus at least on trying to work with the algebra involved. Make sure you're comfortable with that. And then we can spend more time either in person or online talking a little bit about how to picture it in your head and develop more of a conceptual understanding of what we're really doing with these numbers. Making sure you get lots of practice overall, and that concludes our first unit.